Hello everyone, and thank you for joining this webinar. So we started just a few minutes late. Just wanted to make sure that most people have joined us. We're still waiting for a few others, but hope they can join in a few minutes. We'll go from there. As I said, thank you very much for joining. We reckon it's going to take about an hour and a half, so it's about 3:30. It shouldn't take much longer than, or hopefully not take any longer than that. If you can, just make sure you turn your phones and particularly microphones off, although you should be able to mute everyone. We all know what technologies like, we sometimes forget that someone's got a lot of background already, I think, so if they can, that'd be great. Just so you're all aware, this meeting is going to be recorded, so if anyone's got a problem, then please advise us straight away, but the plan is to record this. We'll then send the link out to you as well, so you can actually sort of come back and review anything that you need to or pass on to your colleagues. If you have any questions during the presentation, if you can use the Q&A icon at the very top, it should be at the top of your screen next to chat. If you can just type it in there, we'll then read these out to Jan at the end of the presentation. So we'll leave it to the very, very end. If there's something that's absolutely desperate and you need to ask it, use the raise your hand icon or the chat icon. We'll try and pick up as we can. But apart from that, thanks again for joining. I will hand you over to Jan, my colleague at Lightigo, and we'll go from there. Over to you, Jan. Thanks very much.
So again, thank you for introduction. And my name is Jan Novotný. I'm from the Lightigo company, and I'm one of the co-founder and a product manager at this company. Today, I would like to show you a presentation about our main product, the Firefly system, which is based on the LIBS technology. The content of the presentation will be few initial slides about our company. After that, description about our technology, the laser-induced breakdown spectroscopy. And the second half, I will show you the parameters of the Firefly system, its components, its capabilities, a few of its applications. I will show you the software, and at the end, I will show you live how the Firefly system looks like, how the housing looks like, the exterior, the workstation looks like, and that's it. So let's move on. Lightigo company, so we are based in the Czech Republic, in the second largest city, in the Brno, and we have been founded 4 years ago. You can see here our 5 founding members. All these guys came from the university ground. Actually, 4 of these, one is from the business sector, and we are developers and scientists from the Laboratory of Laser Spectroscopy at the Central European Institute of Technology, which is based in Brno. This laboratory has a long-term experience with the LIBS technology. Actually, still, this is our kind of alma mater, and we are still in very close cooperation with this university and with this laboratory. The head of the laboratory is Associate Professor Pavel Kořiska, and the research group leader at the CETEC is Professor Joseph Kaiser. Both these guys are co-founders of the company. This laboratory has a long-term experience with the LIBS technology, and it's quite known in the LIBS community worldwide. We have also hosted a worldwide LIBS symposium here in Brno 2 years ago. And about Lightigo and our focus. So based on what we have been doing all the time in the Laboratory of Laser Spectroscopy, we are producing now the analytical instruments for rapid multi-elemental analysis and chemical imaging. The main 3 functions or key capabilities, let's say, of our instruments are these 3. The first one, the systems are able to give you a multi-elemental results. Utilizing one result, one scan, you get complete analytical information about the chemical composition. The second one is the capability of elemental imaging. The system is able to analyze spots as small as few tenths of microns. And if you cover by this measurement some area of the sample, you can get a representation or visual representation of the distribution of individual chemical elements. And you can make these chemical images in the software very quickly. And the third capability is the capability of depth profiling, because our technology is destructive, actually a micro-destructive, because the measurement spot is ablated utilizing the pulsed laser, but the destruction is small at the level of tens of microns. Still, it is destructive. So if we do multiple measurements at the same time, at the same position, we are actually digging deeper and deeper into the material. So this way we can analyze individual layers of the sample. And this is about the chemical imaging. So again, if you have some sample surface, you cover the sample surface by a matrix of measurement. You can then make so-called chemical images or chemical maps. As you can see on the image right here, this is the cut of the galena stone, and we make an area scan on this cut, and then we could be able to create a chemical image of lead. More about this later. So chemical imaging and depth profiling are two of the three main capabilities. As you can see, in case of depth profiling, we are detecting here at the x-coordinate in this graph. On the x-coordinate, it is the depth of the analysis, and on the y-coordinate, it is the signal of the particular chemical element. For example, as you can see, the blue dots belongs to the zinc, and at the few initial layers of the sample, you can see a strong signal of the zinc. Then if you go down deeper into the material, the zinc signal is dropping down, and the signal of the substrate elements like iron and chromium are increasing. So this is what the depth profiling is about. By the way, the depth resolution, I mean the resolution in between individual steps, can be at the units of micron, and maximum thickness, which can be analyzed this way, depends strongly on the configuration of the system, and you can expect something between 100 microns up to 1 millimeter. And why this is possible? What is the core technology of our system? Core technology is the laser-induced breakdown spectroscopy. Acronym is the LIBS. LIBS is actually the combination, the very efficient combination of the laser ablation at one side and the atomic emission spectroscopy at the second side. So at the beginning, we are focusing the high intensity pulsed laser. Actually, the pulse length is usually at the nanosecond scale. The focused laser creates very high irradiation at the sample spot, at the spot on the sample surface. And this high irradiation heat the sample, ablate the material, and creates a microplasma. The material is vaporized and ionized, and at the end, the small microplasma, like a spark, is created. It's here, the second step. And at the moment the laser pulse ends, the microplasma starts to cool down. And during this process, it emits the energy to the surrounding area, usually at the form of light, of electromagnetic waves. And that is something we are waiting for. So this is the atomic emission spectroscopy part. So we are capturing this radiation, and we are able to detect the individual atomic emission lines and ionic emission lines. And this way we can say what particular chemical elements are presented in the microplasma, and thus which chemical elements were presented in the original matrix sample. It is good to know what are the benefits of the LIBS technology. As any other analytical technology, LIBS is not solution for everything, but it has a number very handy benefits. So these are these benefits. The measurement is basically very quick. Laser pulse, the length of the laser pulse can be few units of nanoseconds, even less than that. Even femtosecond lasers are used for the LIBS analysis. Then the capturing of the plasma radiation takes few microseconds. So at the fraction of seconds, you can get a complete analytical information. LIBS is sensitive to the most of the chemical elements. And it is especially good to know that it is very sensitive also to the light elements, including lithium, beryllium, sodium, and so on. Limits of detection can be expected at the level of units up to hundreds of ppm, but of course this is strongly dependent on the chemical elements what you are looking for, and especially of the matrix of the sample. In this part, I can say that LIBS is not able to reach such a good limits of detection as, for example, analytical techniques based on mass spectroscopy, but still it is sufficient for many applications. LIBS is a resource-efficient technology. The only thing you need for the analysis is just the electricity. You don't need to consume some gases. You don't need to make a vacuum in the system. All these steps, if you do them, if you use an inner gas atmosphere during the measurement, you can reach better signal-to-noise ratio, and thus you can reach better limits of detection. If you use an inner, that's actually it. So for the basic LIBS analysis, the only thing you need is the electricity. So it's a very resource-efficient technology. Another benefit is that the instrumentation is quite simple in the meaning of the configuration. So the LIBS technique can be adapted to the particular application in the industry, in the extra laboratory conditions quite easily. It is even possible to make an in situ analysis utilizing some portable LIBS devices, and the remote analysis at some units or even tens of meters at the distance. I'm sure you know the Curiosity rover or Perseverance rover on the Mars. Both of them are using actually the LIBS technology for remote detection of geological samples. Another benefit is that you actually don't need any special sample preparation. You can take whatever sample you have, put it in the instrument, and make the measurement. It is not necessary to make some cutting, pressing, putting some metallic layer over that or whatever. It is not necessary. LIBS is able to measure any sample as it is. It can even don't have to be a solid sample. It can be a liquid sample. It can be a gaseous sample. But the truth is that if you make some sample preparation, you can enhance the limits of detection. And last but not least is the high spatial resolution. You can focus the laser, the pulse laser, into the spot which is as small as approximately units of microns. This is quite an extreme. Typical value is tens to 100 microns. You can go down to the units of microns, but in this moment, you have quite a weak plasma and quite a weak signal. So then you are facing the potential problems with the limits of detection of trace elements. So these are the benefits. And now about the quick and very simple comparing to another analytical techniques. As you can see here basically what are the strong points of the LIBS. LIBS can be very quick in the analysis, and it is especially useful for the chemical imaging where you are performing the scanning. So you need to perform a very high repetition rate of the measurement. So LIBS is dependent on the repetition rate of the ablation laser and on the maximum repetition rate of the spectrometer with the detector. Typically, this can run at tens or hundreds of hertz, but it is possible also to make a multi-kilohertz repetition rate. Limits of detection, they're not supposed to be the green background here. That's the typo. Also, limits of detection as opposed to the ICP-MS system, it's not the benefit. You can expect a better limits of detection for most of the elements with the ICP mass spectroscopy. But another LIBS strong points of the LIBS are cost effectiveness, not only about the purchase of the system, but also the running cost of the system. capability of depth profiling, and of course the remote detection. None of these other three technologies is able to make a standoff remote detection. About the application areas, as you can see, the flexibility and the benefits of the LIBS technology enable us to occupy quite a wide field of different applications. I will go very briefly through some of them in these slides. So in the field of metals or metallic industry, the application lie usually at the depth profiling of the multi-layer materials and characterization of coatings, especially in the automotive industry in case of anti-corrosion coatings. Homogeneity check, defectoscopy, detection of the level of corrosion of the various materials, quantification of carbon and alloying elements in steels, and especially aluminum or scrap sorting. I would like to highlight this application because this is a strong field of the LIBS analysis where there are recently quite a lot of application in the industry where the very capable and flexible small LIBS instruments can be mounted directly above the conveyor belt and make a very quick analysis of aluminum scrap or generally metallic scrap, which is running on the conveyor belt below the LIBS unit. Another field is the industry of the plastics, classification of the polymers in the field of circular economy. And this is something we have also faced in the past, the detection of the heavy metals in the plastics, and especially in the recycled plastics. Because more and more recently, there is an effort to utilize recycled plastics materials for production of new products. And these recycled plastics usually came from some black mass mixing materials. And so it is potentially full of potentially toxic elements like heavy metals, cadmium, mercury, and lead, and so on. So the companies which are engaged in this industry needs to respect the rules of the European Union about the maximum allowed content of these elements, and thus they need some system which is able very quickly to detect and determine what is the concentration of these elements. And in connection with this determination of toxic elements in packing materials, input-output quality check, it can be, say, in general, input-output quality check of materials, not only in the plastic industry, but also in other industry. Another two application areas which are strongly researched here at the university ground are in, in the Brno, is the analysis of organic tissues and the field of biology. In the field of organic tissues, it is the detection of the biomarkers utilizing the nanoparticles. So there are nanoparticles injected into the tissues, and LIBS technology can do a very quick imaging, chemical imaging, and creating the chemical images about where these nanoparticles are concentrated in these organic tissues. LIBS is used in the field of research, also in the cancer research applications, and also in the chemical imaging of hard tissues like bones, human bones, and teeth, and so on. Also for determination where individual elements are stored in these tissues. In the biology, it is the detection of heavy metals and toxic elements in plants, the diagnostic of fertilization of the soils of the plants, so detection of phosphorus and other elements typical for the biology and for the field of the agriculture. Determination of the nutrition elements in plants and soils, and also recently detection of microplastics in biology samples. And I could have spent here much more time giving you individual slides of these particular applications, but this is supposed to be only the brief overview of this technology and of our instruments. So let's move on. The last field I have prepared for you is the geology applications, because historically, from the very beginning of the LIBS technology, which was approximately 30 years ago, the application in the geology are the most intensive studied and most intensive used. So in this field, you can use LIBS for real-time online classification of rocks, individual minerals and their variations, the structural analysis of rocks, investigation of inclusions, investigation even the fluid inclusions, for detection of the rare earth elements, both the standard and the light elements, light rare earth elements, also the detection of light elements, as I said already. In the field of mining, the LIBS is very intensively tested in the last 20 years, so it is perfect solution for scanning the drill cores. Gemstone validation is a very interesting application. I will show it to you in next slides. And also utilizing LIBS as a tool for correlative imaging with some other techniques, like, for example, computed tomography, Raman spectroscopy, or the chemical analysis in the scanning electron microscopes. Lithium detection, this is from the field of light elements detection. I have on the separate slide because this is very promising field for the LIBS application, where is actually LIBS very intensively used recently. We have also made some tests. I will show you some images at the, later in the presentation. And it was for the analysis of spodumene and for the analysis of for the battery industry. And yes, many application goes for the lithium battery industry. Many companies are contacting us to search for the solution, how to efficiently detect the concentration and the distribution of the lithium in their samples. So this is something which is this is nice application for the LIBS technology, because the LIBS is very sensitive for the lithium, fortunately. So LIBS can detect lithium not only in the solid samples like spodumene, lepidolite, metalite, and so on, but it can be also used for some dusty samples analysis, or even for the liquids, but it would require a slightly different instrument than the Fireflies. I will talk about it later. And it is usually all these application, or most of these application, belongs, of course, to the field of battery production. No matter what part of the battery production it is, from the mining to the final from the mining of the lithium to the final detection of the battery cathodes and anodes. Another application we have been facing recently is the detection of individual elements in the gems, and especially it was about the detection of the beryllium. I'm not sure if you know about this, but there is a very interesting thing in the field of gem industry, and it's about the sapphires. Because there is, of course, the color of the sapphires influence the price of the sapphires, because the color tells you about the origin of the sapphire, of the gem in general. And in case of the sapphire, if the color is yellow, it's or kind of a yellow tint color, it's a kind of expensive sapphire. But approximately 15 years ago, very clever people actually found out that if they put some beryllium into the sapphire artificially, the sapphire also gets the yellow color. So it was kind of a problem, because this yellow sapphire was used as a fake sapphire on the market, and that was a problem. And another problem was that there was actually no analytical techniques which was able to detect the light element beryllium in the sapphire. And that's when the LIBS came to the game, because LIBS is perfectly sensitive for the beryllium, and it's not definitely a problem for the LIBS to detect the beryllium into the sapphire utilizing one small shot into the side of the sapphire where there is a possible to make shots. So from the time, if you have kind of a certificate from the GEM, there is a special column, special line, which tells you whether this sapphire was tested by the LIBS technology or was not tested by the LIBS technology. So you can be sure whether the yellow color is due to the artificial treatment by beryllium or it is given by the valuable origin. Another interesting example of utilizing the LIBS in the geology is with the combination with the microtomography station, which we have done a few years ago, because at our cooperating university, there is also quite a large tomography laboratory. And so we put together the LIBS analysis and the micro CT analysis, and we was able actually to make like a 3D chemical images. Like you can see here, the LIBS gave us an information about the chemical composition of individual components of the stone. So we have made a cut and we have made a chemical image of the cut, and we have been able to identify what elements are individual components of the stone. And then computed tomography made a 3D scan, so we can then we're able to join these two information about the 3D structure and about the chemical composition to create this 3D chemical image. And now what we can offer to you in this field, in very interesting field and capable field of the LIBS analysis. So our products are basically divided into the three groups. The first from the left is the Firefly system, which I will be talking about later about the slides. And this system is intended for the research, primarily intended for the research institutes and the university grounds and research and analytical laboratories. It has no specialization. It was designed as the versatile unit, which is able to measure almost everything, which can be fit inside, of course. So the priority here is the high performance, full featured, so you can get all the LIBS benefits in one package, and the versatile applications. Another two product branches, which you can see here, are the industrial fly system, iFly system, which is actually the modified version of the Firefly system with some specialization. So this system is perfect for some specific application in the industry. So its performance is focused. But at the same time, the system can be cost efficient and can be, of course, very robust for that particular application. I will tell you about the system in some other webinar. And the same stand for the MiniFly system. This is the small LIBS platform. We call it MiniFly. And this is also intended for industrial customers or for some special applications. The priority of the MiniFly system is its portability, its capability to make standoff analysis at some distance, its adaptability, and of course, cost efficiency. So the lowest cost solution. And we have quite a lot of potential applications for this system. It can be on one side for the aluminum sorting. It can be on the second side as a portable system for the space applications, for the remote detection for the space application, which is something we are currently engaged in. And last but not least, we can use it as a demonstration unit for demonstrating the capability of the LIBS technology itself on some conferences, on some exhibitions. But let's go back to the Firefly system. This is how the Firefly system looks like. I will show it to you again at the end of the presentation on the live streaming. The target segment is the analytical laboratories and research laboratories. Of course, the system is not actually portable. It's a standard laboratory device, as you can see. The priorities, versatile applications, comprehensive hardware and software features. So whatever you need for most comprehensive LIBS application in your laboratory. Now let's go through what are the key points. Yeah, it is the question. Sorry, I didn't hear you. No, maybe.
I don't think it was at this end, Jan. Jan, I don't think so.
Okay. So let's continue. So now I will show you on the following slide. So what is the equipment and what can you expect from the Firefly system? So Firefly system is intended for analyzing of the solid samples. Let's go back here. You can see here are the door for the interaction chamber where you can put the sample. Before I was talking about the various application of the LIBS technology even for analyzing of the liquids or gases. This can be also possible with the LIBS in general, but not that easy with the Firefly system. Firefly system is intended for the analysis of solids. And for this purpose, if you put your sample into the Firefly system, there is, of course, the sample view and manipulation units. You have there a microscopy unit and the 3-axis motorized stage. So utilizing the motorized stage, you can very easily move with the sample in the software interactively by clicking into the picture. I will show it to you later on. The travel range is 10 centimeters to all directions. And this is also the maximum scanning area for the LIBS analysis. So you can put there quite a big samples into the chamber. The step resolution of the motorized stage is below 1 micron. And the maximum speed, which is also the maximum speed of the scanning, is 20 millimeters per second. In the part of the microscope, because of course, if you would like to make an analysis, you need to have a clear, sharp picture image of your sample surface. So you can very easily find the spot for your analysis. And that's why we have integrated a very capable microscopy unit. There is a motorized objective turret, as you can see here. There are 4 positions, so you can have 4 different objectives with different magnification, with different field of view. In standard, we supply plan apochromatic objectives, so you have very clear, unblurry image of the sample. And you can change the objective for whatever you want, because the dimensions and the screws are standardized. So you can use there a Nikon objective, Olympus objectives, or whatever. We are using method-dual objectives. There is a dual sample illumination, so you can have a diffused kind of illumination, which is done by the side illumination lamps. And there is also one collinear illumination, which is perfect for glossy samples. So this is kind of a bright field illumination. And there is also a feature which is known from some professional microscope unit, an image sticking feature. Because as you can see here, this is one of the, this is how the sample view looks like in the software. So you can see the field of view, let's say 2 millimeters. It of course depends on the particular objective which is used. And if you have some big sample, it can be quite time consuming to search your point of interest. So that's why we have integrated this image sticking feature. So manipulator stage goes automatically on some specified area, sticking all the images together and creating one very big, large overview image, as you can see here in the background. And of course, it takes some time, so it is good to make it at the beginning. If you put there the sample, you select the area, start the image sticking, and it will create the wall one overview image. And then you can much more easier find on your sample surface the point of your interest. If you have your point of interest or area of interest, then you can specify how you will be measuring the sample, how you can do how you will do the analytical measurement. So there are three basic types to cover whatever you may need. There is a basic multi-spot measurement. So you can pre-select multiple spots on the sample surface and then start the measurement at once. So system will make a measurement one individual spot after another. Then there is a chemical imaging. So it's kind of area scan. You cover the area, select the area of the sample surface, define the number of measurements, the step size, the resolution, and so on, and start. And the system scans all the area and show you the chemical image. And the third one is the line scan. Sometimes it is necessary or simply more efficient from the time point of view to scan along some line, along some boundary, for example, or through some boundary. So for this application, you can define the line scan, and it can be even a polygonal line, as you can see here. Then you press start and the system just go along the line, capturing the data. And at the end, you get the result. And the result can be in the form of the spectra, obviously, because the spectra is actually the core data information of our system, of the LIBS technology, where you can see number of atomic emission lines. And utilizing them and utilizing the atomic emission line database, you can determine what chemical elements are present in there. And if your measurement was actually the area scan, you can make a chemical image, like you can see here. At the left side, this is actually on the left side, it is the overview image of the sample. It has been actually created by the image sticking. So this is like a photo of the sample. And on the right side, it is overlaid, is the chemical image. In this particular example, it was a chemical image of phosphorus. So it was created in such a way that in the spectra, you find the line of the phosphorus, you click on that line, you select that line, and click on the create chemical image, and the chemical images on the wall area is created based on the intensity of that phosphorus line. So with the same principle, you can very quickly choose a different line, which belongs to a different element, and wall chemical image is redrawn in the fraction of a second, and you can have a different chemical image. You can scan the area of 10 by 10 centimeters square, and with the spatial resolution typically from the 10 to 100 micrometers. But as I said, it is possible to go even lower than that, but then the limits of detection can be weak for the trace elements. Limits of detection 1 to 100 ppm, but again, it depends strongly on the element, what you are looking for, and on the matrix. And here you can see some chemical images which can be captured by our demo unit at the university ground, where students and researchers are utilizing this system, and we are using them for presentation like this one. Here you can see this is example of the mouse tooth analysis. So this is from the field of heart tissues, and you can see the chemical images of the calcium, magnesium, and even the ratio of the phosphorus to carbon. All these images was captured by the step resolution of 30 microns and a laser wavelength of 10-30 nanometers. So for this particular scan, the femtosecond laser was used. Another example of the mouse kidney. This is from the soft tissues field. You can see here again calcium, magnesium, and the carbon distribution. Here it was with the spatial resolution of 15 microns. And this is the soft tissue, the sample of the human skin. At the left, you can see the image, and here calcium, phosphorus, CN band. With the LIBS technology will provide you primarily the information about the elemental composition, because you are you can see the atomic emission lines in the resulting spectra. But if you make an exposure of the detector a little bit longer, you can even see the molecular band. So you can even detect some molecules, even though LIBS is not primarily intended for detection of the individual compounds, the molecules, but indirectly it can be determined as well. And this is from the field of the geology. Here you can see the lithium-rich ore. This is the photo of the cut. And then we made a quick two-dimensional scan, two-dimensional mapping. You can see the chemical images of aluminium, and here the chemical image of lithium. So you can see where on the sample is the highest concentration of the lithium and when there is none. As you can see, this one was captured utilizing the ultraviolet laser wavelength, 266 nanometers. This is something which also is important to choose a proper laser wavelength for the analysis, because you can basically make any LIBS measurement utilizing one laser wavelength. But there are some applications where if you choose a different laser wavelength, you can reach better results. Typical example are the transparent materials, like different glasses or gems and so, and ultraviolet laser wavelength. It is better to use ultraviolet than infrared, because the ablation efficiency is better with the ultraviolet laser, because it is more effectively absorbed by the material, which is otherwise transparent in the visible or infrared region. And now we got to the equipment of the Firefly system. So to make an LIBS analysis possible, you need to have two basic components inside the Firefly system, and that is the pulse laser and the spectrometer coupled to the detector. We are able to offer a wide selection of lasers and spectrometers depending on the customer's application and depending also for the customer's budget. As you can see, in the field of pulse lasers, we are integrating only the modern and stable and efficient diode pumped solid-state lasers. Many LIBS systems so far are utilizing old-school flash lamp pumped lasers, which are cheaper but are not that efficient, and many times require water cooling and so on. And their lifetime is also very limited. So we are strictly focused on the solid-state diode pumped lasers. Usually we are utilizing nanosecond lasers because these are very time-proven type of lasers with very high price-to-performance ratio and very compact dimension and efficient power consumption and run. But we are also able to integrate more advanced femtosecond lasers, so ultra-fast lasers. Utilizing these lasers, you can have much more cleaner the crater, ablation crater, because in case of femtosecond lasers, the ablation is not of thermal type anymore. So there is no heat which is transferred to the environment of the ablation crater, like it is in the case of nanosecond lasers. In case of femtosecond lasers, the material during the ablation is so fast that the ablation is like a pull-off by so-called cold ablation, by the Coulomb explosion. So there is a minimum heat dissipated into the surrounding area of the crater, and the crater can be very small and very clean. That's why these lasers are used in precise industrial application also, where you need to have a very nice cut and very clean engraving, for example. What we offer in our system is also switching of the laser wavelength, which is definitely not a standard feature in case of other LIBS instruments. So in our system, you can choose directly from the software what wavelength you will be using for the analysis. In case you are analyzing the biology material, you need as high pulse energy as possible, for example. So that's why you will choose infrared laser, 1064 nanometers. Then, at the other day, you would like to analyze some glasses and some parts in the glasses, and that's why you need to couple the laser energy more efficiently to the transparent material. And maybe you would like to have as small spot as possible. All these requirements lead you to utilizing ultraviolet laser. And in our software, you just switch the button and you have ultraviolet laser. The focusing in our system is motorized, and repetition rate typically in our system, it is at the tens of hertz, up to, let's say, 100 hertz, but we can go over the 1 kilohertz in a special application. So again, we are able to equip the system many different ways, depending on the application and the budget. In the field of spectrometer, we are usually utilizing the very cost-efficient, compact multi-channel solutions, which are based on individual Czerny-Turner optical spectrometers. And the detection unit is a CMOS line scan detector. This is a very good solution for most of the application, but if the budget allows it and the application requires it, there is still space to improve the detection limits utilizing more advanced spectrometers and especially more advanced detectors. And this is the case of the Eshel spectrometer. This is simply the different type of spectrometer than the Czerny-Turner. Eshel will provide you high resolution and the wide spectral range at the same time. And we usually couple this spectrometer with more advanced detector, which have kind of multiplying of the signal. It can be electron multiplying, CCD, or intensified CCD detectors, or intensified scientific CMOS detector, which are utilizing a microchannel plate in front of the chip to effectively multiply the detected signal. And again, usually tens or hundreds of hertz of repetition rate, but we can go above 1 kilohertz if the application is okay with the limited number of detected elements. So this is something which can be configured in the Firefly. Except for the basic or core components, there are also some other components with further improve the LIBS analysis. And these are the gas extraction. This is the gas extraction unit. This is the nozzle over here, which is simply intended to suck out all the ablated material from the ablation area. This is for the two reasons. One reason, the ablation material can be potentially toxic, especially if you are analyzing some heavy metals and you are making a large area scanning. So there is a lot of shooting and a lot of dust in the area. So especially for this moment, you need gas extraction unit, which is connected to the box where are the filters and all the toxic elements are captured by the filters. This component also increases the lifetime of the optomechanical components, because otherwise the dust would lay on the optical parts or optomechanical parts, and this can decrease their lifetime. So that's why the gas extraction unit is very important. Another one is the gas purge unit. It is the second nozzle over here. The role of the gas purge unit is to clean the sample surface, because especially if you are making an area scan, the point of the analysis can be influenced by the dust from the surrounding points. So that's why it is necessary to all the time during the measurement clean the sample surface. It is obviously not necessary if you are doing only a multi-spot analysis. And another important role of this gas purge unit is if you connect some inert gas or some nitrogen or whatever, any gas except for the standard air, for the barrier air, you can create kind of local atmosphere around the plasma. And if there is a local atmosphere of helium or argon around the plasma, then you can reach much better limits of detection than if you are using an analysis in the air. This is valid not for all elements, but especially some elements like fluorine, for example, can be very influenced by the presence of the surrounding atmosphere, whether it is air or argon. So at the end, gas purge unit can enhance the limits of detection. And both these components are present in the Firefly system. Another important plugin for the Firefly system is this ablation cell. This cell was intended for measuring the samples which, from some reason, are not allowed to be in contact with the air. Samples which even have to be transported without the air. This was especially the case, for example, the case from the battery industry of electrodes. These electrodes are not allowed to be in contact with the air. So we provided this ablation cell. It is a portable one. It is small. It's like 10 centimeters length and 6 centimeters or 5 centimeters wide. We provide this ablation cell to the customer. He put it into the glower box. In the glower box, he put the sample inside, put the gas in, pump the argon inside, close it, and transport the sample into the Firefly system. You can place the ablation cell directly into the ablation chamber of the Firefly system on the motorized stage and make the analysis without the air. This is one application. And the second application is that you can use that utilizing this ablation chamber, the Firefly system actually is or can be the laser ablation system for the ICP instruments. So you can connect the ICP gas circuit to the ablation cell, gas input, gas output, and when you shoot into the sample, the ablated material is carried into the ICP, into the inductively coupled plasma for the, let's say, mass spectroscopy. So if you already have an ICP system, you can utilize Firefly as a laser ablation system for it. And all these components need to be controlled somehow, obviously. And this is how our control software looks like. I will describe it live later on, but just to overview. We have made the software from the ground because in our company, we have not only the scientists from the LIBS field, but we, of course, have the developers from the field of electronics, mechanics, optics, and software developers. And so we are developing the software from the ground for the last 3 years, and we are still putting new features into it. And the updates, future updates, are for free for our customers. In the control software, basically, you can do the following. You can control the system, control the measurement. There are, if I say it from the beginning, there are multiple user accounts. So every operator, every student, every worker, every whoever is working with the system can have its own account and its own rights. So you can limit some settings in the future to some accounts. So this can be handy in some situations. There are measurement profiles. So if you set the system somehow, laser energy, exposure time, and so on, diffuse, and so on, you can save these settings to the file and you can load them next time, so you can use the same measurement profile. There is an automated logging book. So the system is actually recording whatever is happening in the software and who is doing that. So then you can look into the history and open the previous measurements. You can get the information about previous measurement, what was measured, when it was measured, how long, with what parameters. Then, of course, you can set the type of measurement I've told you about. And at the end, you can get the results. You can get the spectra. You can browse the spectra, pan the spectra, zoom, everything. You can create the chemical images from the multiple layers, actually. You can filter the spectra based on the metadata of the spectra, based on the coordinate, based on the pulse energy, and so on. You can use very interesting statistical tools like peak spectra, maximum spectra, and mean spectra. These are just the spectra which you can overlay over your measured spectra which was measured, and this will tell you something about the statistic information of your measurement. There is also the line database, integrated atomic emission line database. There are both databases, the most comprehensive NIST database. So this is full of various atomic emission lines and ionic emission lines. And there is also a shorter one, which is optimized for the Firefly system and which is created or is being created by us. And there is only a limited number of atomic emission lines, only the most intensive ones. So usually you would be using the short database, but in some specific application, you maybe you would like to prefer the complete database. So at the end, you get the spectra and the chemical image. You can export them, of course, export the images, export the data files to the multiple formats and process them in a different software. The point is that the navigator software, it's the control software for the Firefly, is intended to capture the data, to show you the data, but any other further processing with the data needs to be done in some other software. But more, nevertheless, we are, as I said, we are importing new and new features. And one feature, this will be a big update in the second quarter of the next year, is, as you can see here in the last line, is putting there a customer material database in connection with the quantification and sorting. So currently in the software, you are not able, directly in the software, I mean, you are not able to make a conversion from the signal intensity, which is actually the artificial numbers, to the ppm, or to the percent, to the concentration. Because for this, you need to use a calibration curve. I will talk about it later. And you need to have tools to working with the reference libraries and material libraries and the calibration curves. And that is something which we are working on. It is a big update, and I'm looking forward to show it to you in the next webinar. And at the first view, the user interface might look a little bit too complicated, but trust me, we have designed the interface with the user experience in mind. Actually, we put a big effort on user experience, not only in the software, but also in the Firefly housing and its operation, all the workstation design. But still, there are some applications, and this is actually not the case of the Firefly system because it's intended for the research mostly, but for the industrial application, where you would like to have only a simplified software, only few buttons, everything is prepared and set as a constant in the background, and the user, non-educated user, only needs to put the sample, push the button, and wait for the result. That is perfectly possible because we are still designing the software in such a way that it's quite easy for us to put there like a new layer of the graphical user interface, which is much more simplified and is focused only for some specific application. So what you see here on the right side is a simplified version of the software. it was actually developed for the plastic industry for determination of the heavy metals in recycled plastics. And this run on the touch screen. So all the buttons are big, so it can be controlled by touching the screen. And every settings of the system is predefined and set in the background. Or actually, if you log in as an administrator, you have an access to all these settings. But typical operator, which is only partially educated in the analytical chemistry, actually doesn't have to be educated at all. Just put the sample there and select the predefined type of measurement and put the start. Then he is watching at this progress bar, as you can see here. And at the end, only the final information, no spectra, no chemical image, just the information whether there was a cadmium above the threshold or whether it was below the threshold, whether the sample is okay or not okay. So this is something we can do. Because Firefly is intended for the researchers of many types, and these are supposed to play a little bit more with the results, with the chemical images, to make some filtering and process the spectra to get from them better results. We are offering a third-party software. It is actually developed by the Epina, and it is resold by us. It has, of course, our label, Lightigo Image Lab, but it's built upon the Epina Image Lab software, which is high-performance software for processing the chemical images. So yes, it would take me another series of webinar to show you how to work with the software. This is something we supply together with our Firefly system as a tool for editing and processing the chemical images. About the configuration, so as you saw, we are able to integrate a different type of lasers, spectrometers, into the Firefly system. So to make life a little bit easier for our customers and distributors, we prepared a 3 basic configuration. As you can see, the Firefly Core unit, Firefly Pro unit, and Firefly Sci as a scientific unit. As you can see, there is actually no visible difference between these 3 images, and that was our intention. All these 3 configurations have the same housing, the same frame, and they even have the same software with the same features. So the first is the speed of the analysis and the detection limits. So it means that actually differs in the selection of laser and spectrometer with the detector. And of course, some motorized features, because, for example, Firefly Core unit does not have a motorized objective turret. It has just one objective, okay? So this is another thing where they differ, but mainly they differ in the laser and spectrometer, which means they differ in detection limits and the speed. But since they have a same body, same housing, it is quite easy for the customer to make an upgrade in the future. He can start, or you can start with the Firefly Core unit, which is a very reasonable price. And later on, if your budget allows it, you can upgrade. You can put another wavelength into the system very easily. Most of these implementation can be even done remotely by the customer utilizing our remote guidance. You can even change the spectrometer for the more sensitive one, for the faster one, or whatever. That's why all 3 bodies are the same. Okay, so that was actually all for the initial presentation about us, about our about the LIBS technology which we are using, and about the Firefly system. But as you saw in the middle of the presentation, there were more products than the Firefly system. There was an iFly system for the industrial customers. There was a mini-fly system for a special application. But since we are in the core, the development company, all our system has been developed by us from the ground. And so we are engaged also in the custom development of the system. So we can not only modify or customize one of our 3 systems to your application, but we can even develop an entirely new one. Here in your table, in this table, sorry, you can see what you can expect actually from the LIBS in general, what the custom developed system, what can be the parameters of the custom developed system for your better imagination. But if you have some idea about a custom project, please don't hesitate to contact us, and we can discuss the development together and the parameters and the price of the development, of course. Limits of detection basically is still the same, but it is good to know that especially in the case of standoff analysis, when you are detecting elements at the distance of 20 meters, for example, the limits of detection are obviously go higher. Spatial resolution 10 to 200 microns. Again, at the standoff analysis, you can get like a 500 microns spot size. Yes, the variation of these parameters is big in the meaning or in the case of custom development. Repetition rate over 1 kilohertz is not a problem in custom development. A resolution of depth profiling units of microns, maximum depth of analysis hundreds of microns, and a maximum distance of the standoff analysis 10 to 20 meters. But we have done LIBS measurement up to 100 meters in our testing facilities. So this is perfectly possible, but unfortunately the limits of detection at this distance are not suitable for most of the trace elements. So only this was about the custom development. So this is all from the presentation, but let me add some few more slides, because something you will not see in the live software, but still I would like to inform you about that. And that is the quantitative analysis that I was talking about in the software slide. So currently with the software, you can get the spectra and you can get the map and you can export these results, but you are not able to make a pure quantitative analysis. This is something we are working on. And this is here you can see how it looks like. It's not integrated into this part of the software. It's in the beta mode. So it will be released at the second quarter of the next year, but only what you can expect. So the quantitative analysis will be another branch which is stated here at the left. There is another branches which are currently there is the logging book and the measurement screen. The measurement screen is the main screen. Quantitative analysis will be another branch here. Here, you will have the capability to load your reference spectra, because LIBS analysis, and this is the case, the same case as in the case of other many other analytical devices. If you would like to do a true quantitative analysis, you need to have a calibration. You need to have a calibration curve. So basically, you need to measure samples where the concentration of your required or desired element is known. And if you make the measurement of these samples, you can then make a calibration curve. And if you have calibration curve, you can make the quantitative analysis of the sample, which has the same or at last very similar matrix as your reference samples. So what our user interface will allow you is you can measure the reference spectra, you can save them as a material, you can put to them the information about the concentration, which is known for the reference spectra. And this way, you can create a calibration curve, as you can see here at the second part of the user interface. And you can then apply this calibration curve, which can be saved. you can apply this calibration curve in the future to whatever measurement you do. And then you can make very quickly and easily the quantitative analysis. So there will be a custom library, selectable reference library, saved load, a capability to save load reference library, save the calibration profiles. Included in this package, update package, will be able a basic processing of the spectra, like a standardization and the advanced background subtraction. So this will be a big update for the next season. Of course, free for all our customers. And now I would like to switch to show you how the control software looks like. Now I'm sitting in the front at the workstation of our demo Firefly unit at the university ground here in Brno. And I have turned on the Firefly system and put there some sample, which is here, which is the concrete sample. And I will describe you the basic interface of the software. As you can see, I am currently in the measure branch. This is the main branch for performing the measurement. Here is the logging branch. This is the logbook, as I described to you. Here you can find the history of measurement in this system. You can click there, look who was measuring when, what measurements, what type of measurement. You can even load the spectra and explore them and so on. And here will be the quantitative analysis branch in the next update. So, but let's go back to the measure. So the measure screen has been created so the user or operator have an access to all components of the system. Every single part of the system can be controlled in this user interface. And it is divided basically into the 3 groups at the left side. And these groups respect the workflow of the user. So at the left side, this one, it is the group about the microscope, about the observing or exploring the sample surface. So this main window is the sample view. This is just a microscope looking at the sample, and you can see I can move in the sample simply by clicking at the individual parts of the sample, like this. I can change a lot of things here. I can change the objective because there is a motorized objective turret. Currently, I have multiple objectives here, and a few of them are dedicated for the laser, like this one. This objective has very poor imaging capability. As you can see, the image is quite blurry. And that's because this objective is not intended to be used as a microscopy objective, but on the other side is specialized for focusing the laser. So it can focus the laser quite precisely. This particular objective lens is a so-called a macro lens. So it is not doing a microspots. This one has a priority on the long depth of field. So it is able to be adapted more easily to a raw material surface. So at least one of the lens in the objective turret is intended for the laser, and the rest of them usually are intended for microscope, for observing the surface. So let's stick with this 2 magnification objective, and I can go through this sample surface, watching to some holes in there. And of course, I can also use the stage control here. I can move utilizing these buttons to moving left, right, for a specific step, which can be set here, up, down. Here, I can focus or defocus system. And I can, of course, go to some specific coordinate. So I have the capability here to go to an absolute coordinate, X, Y, Z, or for the relative coordinate. But usually everybody's using very easy and intuitive clicking into the image. This field of view, I can measure it, is approximately 3.5 millimeters. Okay, and this is quite a large field of view compared to, let's say, a typical microscope field of view, but still it is quite narrow, especially if I have there a stone like this one. As you can see here, this is the stage view. Stage view is watching on the sample from the side, so you can see whole sample as it is placed in your ablation chamber. And this sample is approximately, I think, 6 centimeters or something like that in diameter. So finding my spot, desired spot, can be like annoying and time consuming. So that's why I have here another window, and this is the overview window. And I can put it here. I can create an area and start an image sticking procedure. So what it does now is that the manipulator is going one step after another, all the time capturing the current sample image from the microscope. And if you wait for some time, you will get a big overview image where you can find your spot of the analysis now and for the future much quicker and easier. So let's wait. I can describe you another thing in the meantime. So the left side is about observing the image and finding your spot of interest. And in the middle part, at the top of the middle part, there is a system configuration. So here you can set the basic parameters of the measurement. Practically it means you can change the pulse energy, you can change the laser wavelength, you can even change what laser focusing lens will be used in your measurement. You can change the focusing of the laser. So from some reason, you don't want to have the laser to be precisely focused. You would like to have a larger spot. It is especially useful for cleaning shots. You want to clean your sample surface before actual measurement, so you can defocus the laser, make an area scan without the spectra, just to clean the area, and then you can focus again. Here, as you can see, you can switch on and off the gas purge. So if there is a gas cylinder with the argon connected to your Firefly system, you can turn it on, and it is not turned on immediately. It means that it will be turned on during the measurement. The same stands for the gas extraction. It's turned on. It is advisable to be turned on during every measurement. And here you can set the parameters for the spectrometers. There is an exposure delay, exposure time. If you have a multi-channel spectrometer integrated, you can select what channels need to be active during the measurement, because sometimes you are interested only for a narrow wavelength range. For example, you are searching for one specific atomic emission line, and you are making a mapping. And if you are doing a mapping and you have like 1 million of shots, then you have like a chemical image, which can be like 10 gigabytes of size. So it is quite, it's not easy to deal with such a big file, to move them and send them through the internet and so on. So it is useful to have a capability to export only a narrow part of the spectra and handle only the data you are interested in and not the rest. So that's why you can switch on and off some of the channels. And of course, at the end, you can filter the spectra and export only the filtered wavelength. So that is another way how you can limit the data file. Each of these components has its own settings, of course, where you can set a lot of things. So as you can see, there is quite a lot of things to be, which can be edited. And so that's why there are multiple user roles. So I'm now logged in as administrator. So I'm seeing everything and I can change everything which I need, obviously. But in case some student is going to measure here, and I can switch the account to the operator, and many of these options are not visible or cannot be changed. Okay, and back to
Jan, it's Matt here. Just conscious, we've only got sort of about 10 minutes or so left. Okay.
Okay.
So just be aware of that, please. Okay.
Okay. So I'm sorry.
Thanks.
I'm sorry. I will try to be much quicker. So this system overview, as you can see, you can very easily go to some coordinate very quickly, like here, and let's go for the analysis. So at this measurement part, you can choose the type of measurement. So you have multi-spot, line scanning, and so on. So I will jump into the mapping. I will make an area for the scanning like this one. It will show me how many spots there will actually be. I can change this. I can change everything here. I can change the step size in one coordinate, in second coordinate, and so on. I can even switch to another type of mapping. It's called the standard type of mapping, where I can select how many shots there will be on each spot. So everything is possible here, okay? But to be quick, let's go for the fast scanning. So the system will now scan this area. So the system is scanning. I hope you can hear me, even though the gas extraction system is running and making some noise. And here at the secondary camera, you can see what is happening there. The sample is going from left to right, and the laser is shooting at 50 Hertz and scanning during the time. At the right side, you can see how the spectra are captured. At the bottom, you can see the measurement progress. So now we are at the half approximately. We will end at 20 seconds.
Just while this is completing, if anybody does have some questions, please feel free to start typing them into the Q&A box at the top of your Teams windows. So feel free.
Okay, now you can see that I have made some new craters, but they are really small craters, and especially in this moment of in this application of a hard sample, like this piece of concrete, the craters are barely visible. I can switch to the mode when I can look at the spectra. You can see there is a lot of atomic emission lines here, and you can use the atomic emission table to give you advice on what atomic emission lines you are actually watching. But let's switch to observing the chemical image. So as I described to you in the presentation, I can select somewhere here some atomic emission line, for example, this one. Okay, I have put, you can see it here, I have put a small black point. So my chemical image, as can be seen here, is created from that point. And it can be seen that these atomic emission lines were strongly intensive at the right side of my chemical image, of my map. On the otherwise, if I click on some other, or I can even move continuously with the point, and chemical image is redrawn during that process. Okay, I will try to find some other atomic emission line which has a different chemical image. Yeah, and you can see that each point, each atomic emission line has a different chemical image. This chemical image is a low resolution one, as you can see. I just wanted to show you a quick chemical imaging. And you can, of course, change the color representation. You can change the histogram of the image to change what you can see, to highlight the differences. You can click on these images and open the spectra which belong to that point, as you can see here. And at the end, you can export all these and process it in another system. We have no time, unfortunately, so I will quickly jump into the live view, and I will show you how the Firefly system looks like in the laboratory. So just a second. Well, that's me in the lab. So this is the workstation. The table has been designed exactly to fit into the Firefly housing, so it is supplied with the Firefly system. We are using ultra-wide screen, as you have noted, so this is perfect screen for presenting the spectra and the atomic acquisition line, and this is the body of the Firefly system. The most important part is at the top, the control panel with the stop button. Hopefully you will never use it. And this is the main door. Main door with the laser filters, so you can safely look into the door from the front or from the side. This side window is perfect when you are sitting in front of the PC and you just turn your head and you can see what is happening inside the chamber. We can open the chamber. Big door is open, so you have easy access to the interaction chamber, to the motorized stage, 3-axis motorized stage, and here is the sample, the concrete piece in our case. This is the objective turret, illumination, gas extraction, gas purge unit, and laser comes from the top. Everything is guarded by the interlocks, so if someone accidentally opened the door, actually it's not possible to open the door during the measurement because there is an electronic lock, but still if someone opens some of the door, the measurement stops automatically. There are multiple doors. Here are the service door with the access to the top optical compartment where the spectrometer is placed. This bottom service door are for control electronics, and at the back are again service door for accessing the laser. Here you can see the accessories in the form of gas extraction unit. This is the unit where the gas filters are presented and need to be changed time to time. So this is raw workstation, and all the connectors are hidden here on this side where the table is supposed to be. So monitor, LCD, keyboard, flash drives, everything is easily accessible below the table. So this is all from me. Thank you for your attention. I'm sorry I wasn't more efficient with the time, so I hope next time I can show you next thing and other things, including the quantitative calibration. So now I will pass my word back to Matt.
Well, thank you very much, Jan. That's a great overview, and yes, I know there's more you could go into. I think there's an overview to give people a taste. I think it's actually fantastic. What it's done, it's obviously wowed people so much that they can't think of any questions to ask. So it's pretty in depth. So yeah. So unless anybody wants to ask a question pretty quickly, we will. You know, so I'll give sort of 10 seconds or something if you want to throw a question into the Q&A section. If you can't see that, you're not used to using Teams because now we've all got over COVID, you can put in the chat section if you so wish. Let's have an awkward silence for a few seconds if anybody wants to do that. Okay. I'm going to make the assumption that nobody wants to ask anything at the moment. So I guess, first of all, thank you very much, Jan. As I said, I know you could spend almost days talking about this. So for you, that was kind of quite high level, but I still think it gave a great overview and a great idea with some depth about what the product can do. I'd like to thank everyone that's joined. Really appreciate your time, giving up an hour and a half of your time just for Christmas. We're all trying to wrap work up before Christmas. No pun intended there. As I said, the meeting's been recorded, so we'll send out a link to everybody. It'll be available on our YouTube channel as well, and we'll send some sort of digital brochures and some application notes as well. If anybody has any questions afterwards, most of you got my contact details. You should have my contact details, but you also certainly have it with the email that I send to you. If I don't speak to you before Christmas, have a great Christmas and a happy New Year, and we'll be in touch. Thank you once again, Jan. Thank you, everyone. Take care.
Thank you. Goodbye.